So here we go with Chapter 8 of the Year 2 Mechanics A-level course, so the last chapter of Mechanics. Now, what we're looking at is vectors and kinematics, and what we are used to so far is basically the Suvat equations, all right? Now, in the Suvat equations, let's just take, I don't know, s equals ut plus 1/2 at squared, just as an example of one of them. We know that the s, the u, and the a in this equation are all vectors. But so far, in AS level maths, we just took those vectors as being either positive or negative, right? Are we going to the right or to the left, or are we going up or down? Now, we're going to think of these things as being two-dimensional vectors, so motion can be happening in any sort of direction. So let's say we start here, and we move in that direction. Well, if we move with a constant speed, so let's ignore Suvat for the moment, and we'll introduce a different equation, and then in a second we'll be back at Suvat. If we're moving with a constant speed, then we know that speed equals distance over time, or the sort of vectory way of saying that is displacement equals velocity times time. Now, displacement is the vector version of distance, and it's measured from where we start. So after t seconds moving with this velocity, if we started here, that is the displacement vector. Okay, so there's my displacement vector. We started here and we've got to here. Now the problem is with vectors, we don't always want the displacement to be measured from the starting point. So here's my x and y axis, right? Here's my origin point from which I'm measuring my vectors, and it's not necessarily the same as where I start. Now in all the questions we've done so far, we can, wherever the object that's moving is starting, that is what we sort of call our starting point, right? We measure displacement from there. With the vectors, we might want to measure displacement from the origin on the axes that we're working from. So we start at this point, and now this point can have a position vector. So where do I end up? Where is my position? Well, my position is here after t seconds. Well, so let's imagine that this is 1 second's worth of travel. So after 1 second, we're here. After 2 seconds, we're here. After 3 seconds, we're here, right? So this vector of displacement is in this direction, and it's longer or shorter depending on how long we've been moving. So in that case, how do I find the position vector of this point or this point or this point? Well, the way that you do it is to find the position vector of where you started. So let's call that, well, for position, we're going to use the vector r. R0 is going to be our initial position. So that's r0 for maybe time equals 0 or something like that. And then the distance that we've moved, the displacement, we've already said is velocity times time. So we get this equation. The position that I'm in, so say just here, is my starting position plus the vector that brings me to there, velocity times time. Okay, and that would tell me the position that I'm in. Okay, the position that I'm in at I don't know, when t equals 2 or when t equals 3 would be this position. So r equals r0 plus vt, that is the starting position plus speed times time, right? Velocity times time. Displacement is velocity times time. How far away from this position am I? What's the displacement from this position? And that tells you my current position. So that is the two-dimensional vector equivalent of speed equals distance over time. R is our new notation for position, and position has slightly replaced displacement. The difference is position is measured from the origin of the axes which are defining your vector system, and displacement is measured from your starting point. So Vt is still displacement, but it's displacement from this point here. So if you're displaced from that point there by that much, then your position is that. Okay? So example 1 takes us through that. A particle starts from a point with the position vector 3, 7, or 3i plus 7j, and moves in a constant velocity 2i minus j. Now, I still prefer to write these as column vectors personally. So 3, 7 is my starting point. Moves with constant velocity 2 minus 1. The constant velocity is my cue to use this equation here. Find the position vector for the particle 4 seconds later. So I know that the position vector is r0 plus velocity times time, and time in this case is 4 seconds later, so when t equals 4. So work that out and we get 3 plus 4 lots of 2, 7 plus 4 lots of -1, so 11, 3. And if you like i's and j's, then you write that as 11i plus 3j. If you prefer the working out with i's and j's all the way through, then it's there for you on page 160 in the textbook. Part B, find the time at which the particle is due east of the origin. Now, north, south, east, west. Okay? So due east of the origin, that means, well, let's compare it to this thing. Here's my origin here. Due east of the origin is just another way of saying it's on the x-axis. So due east of the origin or due west of the origin is just the x-axis. Due north or south of the origin is just the y-axis. How do I know that I have a position vector which is on the x-axis? The y-coordinate is equal to 0. Okay? So 3, 7 plus, what time is it? What time is it? When I've been going at this speed from this position. So that has got to equal something and then a 0 in the y position. So 3 plus 2t equals some x position, don't know what that is. And 7 minus t has got to equal 0. Well, if 7 minus t equals 0, then t's got to equal 7, right? So that's example 1. Now the next thing is, our Suvat equations are still going to work, but there are particularly 2 of them that we use. So v equals u plus at. Well, if v is a 2-dimensional vector, u is a 2-dimensional vector, and a is a 2-dimensional vector, that is still an equation that is valid. And the other one is s equals ut plus a half at squared. But you've noticed that instead of s, I've used r because r is our new, r for position instead of for displacement. But those are not new equations. They are exactly what we knew before. Just to remind you, just quickly, because this one's easy to do, acceleration is final velocity, take away initial velocity over time. Now, if the acceleration is constant, that is change in velocity over time. That's the definition of acceleration. You take that and you rearrange it and you get this. Nowhere in that explanation did I say that acceleration is only going in one direction. So acceleration is a vector quantity. That argument still stands. And if you go back to the AS material where we proved all those different Suvat equations with different ways, well, the same arguments apply. We don't, at no point do we need the acceleration or the velocity or anything to be a one-dimensional vector. We know that they're vector quantities and we can manipulate them as vectors and produce these equations. Now these 2 are the ones that they're particularly keen on us using. I'll do one more example here, and hopefully we've got the idea. We've got a particle, in this case, with velocity minus 3, 1 at time t equals 0. The particle moves with constant acceleration. So I'm writing down, when I see the phrase constant acceleration, I'm thinking Suvat. So here are all my Suvat things. U is the initial velocity. So minus 3, 1, it tells us, is the velocity it's moving with when time t equals 0. So that's the initial velocity. The particle moves with constant acceleration 2, 3. So 2, 3. There's my acceleration. Find the speed of the particle and the bearing on which it is travelling at time 3. So when t equals 3, the speed of the particle is what I want, or that is my final velocity, and I don't care how far it's moved. That s there, by the way, maybe I could put an r in this list now. U, V, A, R, and t might be sensible because we're in 2 dimensions. Okay, but this is what we've got. So we'll look through this, and the same as a Suvat equation, I think to myself, well, which equation works? And hopefully I fairly quickly, because now there's only really 2 that they're asking us about, so fairly quickly I come to the conclusion that it's this equation. V equals u plus at. So v equals minus 3, 1, plus 3 lots of 2, 3. And that gives me my velocity is minus 3 plus 2 lots of 3, so that is 3. And 1 plus 3 lots of 3, so that is 10. So there's my velocity. In mechanics, they like i's and j's, so I'll switch back to i's and j's. Now the problem here is they didn't ask me for the velocity, they asked me for the speed. And this probably is the main tripping point in this section. When you are asked for velocity or acceleration and you're in a vectors question, you give the velocity as a vector. You give the acceleration as a vector. If they'd asked us for our final velocity, that would be the answer. We wouldn't need to do anything else with it. If they ask you for your acceleration, you give a vector as an answer. So either a vector that looks like this or a vector that looks like this. If you're asked for the speed Well, the speed is the magnitude of the speed is the magnitude of the velocity. So the magnitude of the velocity vector is the speed. Now that is a really important sentence to get in your head. That's just the definition of speed, isn't it? The speed is the magnitude of the velocity. So the magnitude of the velocity vector is your speed. So in other words, what's the magnitude of this vector? Well, 3 squared plus 10 squared and square root it, just from our vectors knowledge, okay? The other thing it asks is, what's the bearing? Well, remember, bearings are measured from north clockwise. So this is 3, 10, so it's going 3 across and 10 up. That's the velocity vector. So it's going in what direction? Well, from north, it's travelling here, 3 across, 10 up, and measured from north clockwise, that's the angle that we want. Well, I know that this angle here, let's call this angle x, tan x equals 10 over 3. So you draw yourself a little diagram. If you know what the vector is, you can work out the angle it's at, and you can work out the magnitude of the vector just through vectors knowledge. But be a little bit careful with bearings, that you don't leave the answer as x, that you do 90 minus x to get your theta. And I think really all the techniques are there in those two examples. But I suppose, I said I'd stop after example 2. If you want to stop the video there, you can. Let's just do example 3 for anybody that's interested. So an ice skater is skating on a large flat ice rink. At time t equals 0, the skater is at a fixed point O and is travelling with velocity. So the initial velocity then is 2.4 minus 0.6, and I'm leaving it the column vectors because I like column vectors. So given that they've told me that much, I'm going to just go ahead and assume, so I'll put that as R. I'm going to assume that I've got one of these questions. T is 20. So when t equals 20, we're going with the velocity of a different thing. So this final velocity is this, minus 5.6 and 3.4. So there's initial velocity, final velocity, and time we've been travelling for. Relative to O, the skater has position S. Now, what's happened here is they have told us that relative to O, now O is our origin in this case, so we're not going to use R for position, we're going to go back to S because the displacement is measured from our starting point. It says relative to O, relative to the point where we started. So S is that. Modelling the ice skater as a particle with constant acceleration, so if we hadn't worked out that it's a seaback question, there's our clue, constant acceleration. Acceleration is what we're trying to find. So we've got that, we've got that, we've got that, we don't want that, we've got A that we want there. So what equation do we know? Well, the equation we know is V equals U plus AT, and minus 5.6, 3.4, that's V, equals U, 2.4 minus 0.6, plus A, which I'm trying to find, times 20. There we go. We can write these as I's and J's if we want, but from there we can solve that equation, okay? Find the expression for S in terms of t. So now we can go back. S equals ut plus 1/2 at squared. Because we're in two-dimensional vectors, we should perhaps be calling this r, but we're gonna go with S, given that S in this case is our r, isn't it? So S equals ut plus 1/2 at squared, and then just substitute in. So u equals 2.4 minus 0.6. T is 20. Oh, sorry, find the expression for S in terms of t. So t is no longer 20. So there we go. So times t plus 1/2 times the acceleration, which is the answer to part A. So that's answer to part A, answer to part A that goes in there, times t squared. There we go. So there's everything we need to find the answer to part B. The time at which the skater is directly northeast of O. Well, for something to be northeast, well, there's north, there's east, here is northeast. So what's that? Well, it's an angle of 45 degrees here and 45 degrees here, or in other words, it's the line y equals x. So what does that look like? Well, it means the x and y coordinates of the displacement have to be equal. Okay, so the x component and the y component of the displacement is equal. So in other words, when I've worked this out, the number on the thing on the top is an expression in t. That, well, let's just take the answer from the book, shall we? So it looks like. Well, actually, it's not a very simple answer, so never mind. This vector simplifies to something there and something there. These two things are equal to each other, okay? This is something in terms of t, this is something in terms of t. So we put them equal to each other and solve an equation in terms of t. In this case, it turns out to be a little bit of a fiddly equation because it's a quadratic, but we end up with t equals 10 seconds at the end of the example. Now a second skater travels so that she has position 11, so the second skater has a position this, 1.1 t minus 6, 1.1 t minus 6 j. So the position of this person is 0 in the x direction, 1.1 t minus 6 in the j direction. In other words, she's just moving up and down the y-axis relative to O at times t. Show that the two skaters will meet. In other words, the displacement of the first skater has to meet the position of the second skater. So this is a position or displacement, same for the first skater in this particular case. That vector has to equal that vector, and when you put them equal to each other, you'll find that the y components form an equation which you can solve, and if you substitute that t into the x components, so you put this one here equal to 0, then the same value of t that makes that one equal to that will make this one equal to this. Okay, so it's just putting two vectors equal to each other and showing that the equations work. Again, you can do that with i's and j's and equate the coefficient of i's, equate the coefficient of j's, and the example there is in the blue box, page 162. So quite a long video, but I suspect most people stopped after example 2 anyway. That's the end of 8.1.